Thanks for coming. I'm Ben, and I'm going to talk about some tech that we've been building for the last year or so. That's a direct response to the experience that I've had trying to work with a bunch of organizations that have been trying to adopt microservices and do their cloud-native transformations, do their cloud-native journeys. So I'm going to dive in. Most of this talk is going to be a demo, so most of it's just going to be looking at code. If folks have questions, go ahead and ask. And is that all right if they ask questions midway? Yeah. And if I want to defer to it later, I'll just say I'll do that. All right. So for those of you that know me, I spent the last part of a decade helping to push the idea that we should all be building microservice and Lambda-based cloud-native applications, and we should be running them on container orchestrators, and that was a good thing. And I still think that's a good thing, but I think that if you really reflect on what we were doing when we were building container orchestration and a lot of the cloud-native tools, it was focused more so on us as operators, trying to help us as operators do things like turn off machines so we could do hardware or software upgrades, than it was so on making the developers' lives great. And I'm sure you've all heard lots of people arguing that building microservice-based applications is harder than the applications they used to build when they were just building monoliths. And from a lot of organizations that I chatted with, basically we'd hear back from them saying, hey, cloud native made development harder. It made microservices and Lambdas made it difficult to query and mutate my state, which was now separated into all these different silos across all these different teams. Microservices and Lambdas made it harder to consume from the web and mobile. There's a lot more steps to get from the web and mobile to my data, to my services. And monoliths were just plain simpler. People just kept saying this to me over and over again. I just want to build my monolith. It was easy when I did that. Why can't I just do something like a monolith? So we decided to try to build something that made all of this easy again. And we call that Resemble. And it's a software stack on top of gRPC that runs in Kubernetes, if you want to run in Kubernetes. So we're not saying let's throw away the baby with the bathwater. Let's keep everything we've done in the last 10 years, but can we give a better abstraction to developers? And we do that by basically introducing 4 key primitives in this application framework that I'm going to talk about through demo. Okay? All right. So the demo I'm going to be showing you is a bank. Why? Because banks, I think, demonstrate a lot of the challenges that we run into when we're trying to build out our microservices. And to start in Resemble, I'm going to switch to this mode. Great. To start in Resemble, first I'm going to talk about the durability primitive. So in Resemble, what you do is you describe what are called durable data types. Okay? So you don't just describe services, you also describe these data types. You do it to start in protobuf. So we pick protobuf as our IDL. In the future, we might support other IDLs. And since we're building a bank, you can imagine what we might have is something like an account type. And an account would have things like, the name, the birth date, the balance, maybe the last time you logged in, whatever else, right? And you basically use protobuf annotations, protobuf options. If you've never used them, they're just first-class pieces of protobuf. I haven't invented anything new here yet. To signify that this type, this schema, represents a state in Resemble. In addition to describing the state, you then describe the operations on your data types. So in this case, for account, we want to do things like deposit, withdraw, balance, and for each of the RPC operations, we also describe effectively the kind of that operation, whether it's a reader, writer, and I'm going to talk about a few other kinds as I go through the demo. Okay, makes sense? We've got a protobuf plugin that generates some code for you. It looks almost identical to gRPC, if you're familiar with gRPC, which I imagine most of you are. On the left-hand side is gRPC. On the right-hand side is Resemble. I'm going to show you the demo in Python. We currently support Python and TypeScript backends, but we'll support all the gRPC family as we get more users and adopters. So just to walk through a few of the differences, otherwise it's very similar. So very similar to gRPC. First we swapped request and context, and we inserted state. So basically every method gets passed the state of the instance that you've constructed. Okay, these state instances must be constructed. I'm going to show you syntax for that in just a second, and looked up via an ID. Okay, so now I'm going to jump over and we're going to look at some code. So in this bank, you can imagine when I want to construct something like an account, it would look like this. From an account, I'd say construct, and then I'd pass the ID that I want for this instance. And then in this case, I also call a method which initializes it. So in this case, we kind of think of it as a constructor. In fact, that's actually what we call it in the protobuf. Okay? You can also construct these durable data types, in this case, without specifying an ID. If you don't really care about the ID or you want it to be a randomly generated ID, you can just go ahead and construct these types. Okay? All right, so that's construct. Now let's look at lookup. So here, I'm looking up an account. Everyone can see this? Sorry. And then once I have that account, and I've got effectively a handle to it, then I can call RPCs on it, just like normal, by calling balance. So very similar to gRPC, except you're not constructing channels and stubs. It's a higher level API. You're doing a lookup of the specific instance of this state type that you've instantiated, and then you're making the calls from it. Okay? So the basic idea is these types that you describe, when you construct them, they're durably stored within your system. All right. Good so far. That's the first primitive. The second primitive I want to talk about is reactivity. And reactivity actually really comes from the fact that trying to get data out of all of our systems is a huge challenge. And it's one of the things that made it more difficult for people that are trying to build their web and mobile apps. So thanks to the IDL, thanks to our plugin as well, we can generate some code for calling from the front end. So in this case, this app is just a React app. So for those of you that aren't familiar with React, well, I'm not going to go into what React is, but it's a React app. And in addition to just getting the code for being able to make single calls from the front end, we also generate reactive calls. So what do I mean by that? So I'm going to uncomment 2 lines of code here. I'm going to uncomment first the code that we generated. And then I'm also going to uncomment a little bit lower down these 3 lines. And what are these 3 lines doing? So just a second ago, I was in the back end and I was showing you some code specifically in the account balances function. That account balances function is now being called here reactively from the front end. So basically, use is the prefix in the React world for effectively generating a reactive component, a hook, a reactive hook. And what's happening here is I'm saying I want to use bank, which is a different API type. I showed you account. We also have a bank as a durable state type. And specifically, I want to call the account balances RPC, but I want to call that reactively. So if we switch back now to the front end, and I do, okay, you'll see that now we're seeing the accounts, but you're also noticing that the numbers are updating. And what's actually happening here is even though, you know, it looks like I'm just making a single function call here, this is a completely reactive call. So what's actually happening is if I go back to that function that we were just looking at, the account balances function, this looks like just a normal unary call, but what we're actually doing under the covers is we're checking to see all of the different state types that you might be calling into and all the state types that they're calling into throughout your system. And if the state ever changes at any point in time, just like in the front end, if you're using React, if the state ever changes, it will re-render. If the state ever changes in the back end, we propagate that state all the way back up to the front end as well. Okay, so this allows us to still have the composition that we want between different teams, libraries. In this case, I could have a bank and an account. They could be owned by different people. I could be calling into them. But as that state is actually changing, when I'm calling into it, it'll be propagated all the way back up. Okay, effectively, we're creating these materialized views dynamically. Okay, all right, that's the second primitive. Now, I want to take a second to talk about the programming model a little bit here. I mentioned earlier that, you know, it's a little bit different in terms of context, state, and request. The other difference here is that the type of context. So this function account balances was tagged as a reader. And by being tagged as a reader, it means that all it can really do is be reading state. So we don't pass in a normal gRPC servicer context here, like you might have seen on the back end. We pass specifically a reader context, which means the only things that it can call, the only thing that that function can effectively call, that method can effectively call, is other readers. And that's one of the ways in which we guarantee safety here, and we can do this all reactively. Right? So you're guaranteed that all the things you're going to be calling as readers. Now that'll happen at runtime if you don't use something like MyPy. If you use something like MyPy, It'll happen at compile time, and in TypeScript, if you use something like TSC, it'll happen there as well. Okay, so there's a safety hierarchy here that's actually making sure that you compose all of your different functions safely. All right, great. So that's durability and reactivity. I'm going to move on to the next pyramid I want to talk about, but before talking about it in detail, I actually want to give a little bit of motivation for it. This was probably one of the #1 challenges that I ran into in working with organizations that were transitioning to building their cloud-native apps. And it's right in Google's microservices demo as a great example. Has anybody, who's looked at the Google microservices demo? Anybody looked at this before? It's a great place to go to see one of your first examples of trying to build a microservice-based cloud-native app. It's effectively an online boutique, and as being an online boutique, it has what you'd imagine an online boutique would have, which is has a checkout. It has an area where you want to place an order and do a checkout. For those that are really familiar with this, I've changed a few names here, but effectively I'm representing this accurately. So when you look at checkout, and there's lots of code between all these different calls, but this is the main RPC. When you look at it, at first you think this is great. Independent teams can own different services, the catalog service, the cart, shipping, payment, emailer. This is exactly what I want. I get to compose with all these different services to build up my app. But does anybody not like the look of this code? The scary thing for us that have written and run microservices in danger is what happens, of course, after you've called payment.authorizeCharge if there was a failure. And the reality is not good things. And anybody who's actually ever run microservices in danger knows that we can't actually just compose calling a bunch of services together because of these possible realities. So why is the code written like this? Why is Google's microservices demo getting everybody to start writing code like this and then have a really bad time in production sometime later? The reason is because it's the code we want to write, right? This is the nice composition-based code. And developers' intent, of course, is that this gets executed atomically, which is probably the experience that they had when they lived in a monolithic-based stack where they effectively opened some transaction, did a bunch of stuff, and then closed the transaction and completed. And of course, they also want this to happen idempotently. They only want it to happen once. Okay? These bugs are everywhere. I see these bugs all the time. I make it as often as I can. I take screenshots of them. Here's one of my favorites. I was depositing a check. Got a failed to deposit check or okay or try again. Naturally, I wanted to deposit the check, so I clicked try again. 24 hours later, I got this wonderful email. Said we failed to deposit your check. Please give us a call. I gave them a call, and they politely accused me of trying to commit bank fraud, which is trying to deposit my $219 check twice. And I just kind of chuckled and said, we all know what happened, right? Got somewhere in the code where it deposited the check. Then there was a failure. We retried, and it wasn't idempotent. And this is what happened. Okay? So we've had to solve this problem. And this is what we spent a lot of time doing with these organizations that were going through their cloud-native journeys. And we solved the problem with what I call the rise and ubiquity of Q-glued software. So we've effectively taken all of our back-end services and thrown away the really nice programming model that we wanted, which was just being able to call everything compositionally, and said, nope, every time we want to talk to somebody else, we're going to talk to them through a queue. We're going to write to a queue, and then the next thing's going to read from a queue. We're going to write from a queue, and the next thing going to read from a queue. This callback-based approach leads to an inversion of control in your code. It's one of the reasons why all the modern languages have introduced async await, is so you don't have to write callbacks. But we're all doing it in the back end. This is what we're doing every single day. So what can we do about it? So I'm going to show you now another type of method that you can annotate and resemble, which we call transaction. Okay, so we got readers, writers, and transactions. So let's look at what a transaction looks like. Okay, so at the top of the screen, we're doing a bank, so here's the bank transfer. So it's been annotated as a transaction, which means the way that it's going to work is I'm going to look up the from account that I want to take money from. I'm going to look up the to account. I'm going to withdraw from the from account. I'm going to deposit to the to account, and that's it. It's either all going to happen atomically or none of it's going to happen. Now what's really interesting is this is actually not the way you'd write this code. You'd probably do something like that instead. Because we can. Because we know that this is either all the effects are going to happen or they're not. Which has actually been a really, really powerful thing. If you go back and you look at a way a lot of this code has been written, there's no reason why we would call cart.getItems and then later call cart.emptyCart. We're only doing that because we're possibly dealing with failures along the way. We can save an entire round trip time if instead we had a function on cart, something like checkout, that both emptied the cart and returned your items. So there's a lot of actual more efficient ways that you can write the code once you have something like transaction at your fingertips. All right, I want to show you another transaction, which is sign up. So here's another RPC that we have, which is sign up at the top of the screen again. Now the reason I want to show this one is because everything I've been talking about sounds and works great when you're just within the world of Resemble. You're just building your apps there. But what happens when you actually want to call to external services? How does it work then? So to demonstrate that, you can imagine that when you're doing something like sign up, one of the things you might want to do is send an email and thank that person for signing up. So to really drive this point home, we actually construct a new email message. We're using Mailgun here, and send the message before we even open the account and deposit the initial value. Because again, all of this is going to happen atomically or it's not. So there's some magic in what's actually going on here, and I'm not going to spend too much time talking about it right now. But we believe that actually the creation of these integrations can make for an amazing developer experience where I don't have to care about all of the semantics of trying to do this idempotently and transactionally. One person can do it, a library can do it, and then everybody else can just consume it and use it. And that's what we've had to do. And the reality is like a lot of these third-party APIs that you use out there, they're really bad. They don't have great notions of idempotency or transactionality, and so most people get it wrong, and putting this in a library anyway is a good idea. All right. Last one I want to talk about is idempotency. I've mentioned it a few times. To do that, I'm going to go back to the front end, and I'm actually going to uncomment 2 more lines of code, which is now in the sign up functional component, where I'm going to go ahead and I'm going to do a sign up. And I would like a volunteer who would like to get an email from us. And if you don't get the email, don't tell anybody. But if you do get the email, tell everybody that the demo worked. Bueller? Anybody? Anybody? Come on. Yes, perfect. Appreciate it.
Soren, S-O-R-E-N, is a nerd@gmail.com.
I love that this is the one we got.
So one D too many.
Is a nerd.
There we go.
Perfect. Awesome. All right, Soren, let's give you a bunch of money.
Nice.
So before I click sign up, I'm actually going to go back to the back end. I haven't showed you this yet, but there was a tool that we built to actually make doing all this development super easy. It's called RSM. And what I'm going to do on the back end actually is I'm going to trigger a chaos monkey. Then I'm going to come back and click sign up. You notice that once I did that, the numbers stopped moving, which they should because the back end's down. If I go back to the back, we've got these cute little graphics reminding you that chaos is a good thing. At some point, the application restarts, and I go back, and the demo doesn't work, but hold on. Let's see. Come on. Come on.
Let me know when I'm supposed to.
No. I might have just had a bad proxy. Okay, let's try it again. Let's try it again. Soren is, let me do a full refresh, is a nerd@gmail.com. We'll give you all the money. We'll trigger the chaos. We'll click sign up. And we'll hope that we have a proper, I don't know why it says failed to connect here. Well, I'm talking to a code space, and so it's possible. Yeah, bummer. All right, well, let me just tell you what happens, which is the mutation in this case sounds like it's getting a permanent failure, so it's not retrying. If the mutation, it's telling me it's not connected, which I don't agree with, but I think it's this thing. If it's not a permanent failure, we do retry the mutation. We retry mutations as long as possible. Why? Because it's completely safe, because they're idempotent by default. Okay, so that's the punchline with the idempotency. Again, no more like okay or try again. We can just try again, or a user can try again, and it'll just work. except when it doesn't. All right. Okay. So I've been talking a little bit about this tool that we built called RSM that makes it easy to build your apps, your full stack apps. Let's go there. All right. So we got this tool called RSM. It's also what you can use to actually run the app in production. So we've got a variant of it, which is RSM serve. I've been using RSM dev this entire time, RSM dev run. We've got a variant which is RSM serve. You can stick that in a container. You can stick it in a VM, and then you can go ahead and run your Resemble apps in production. And then we've also got an RSM cloud model, which lets you actually run this horizontally. Serve will take advantage of as many resources on a single machine. RSM cloud will take advantage of resources across machines, specifically using Kubernetes. So what's going on there? Well, getting back to that last point that was at the bottom, we wanted to give developers the experience of making it feel like they're building a monolith while they get the outcome of effectively running like microservices. Okay? So what's that look like? If we jump back to the code real quick. Oh, now the email comes through. All right, well, we've reconnected, which I'm thrilled about, and there you are, Soren. You should have gotten an email. All right, Soren got an email. Glad he got the email. Okay, now I'm going to go back and I want to show you in this main.py. This is effectively our entire application. So in this application, we're specifying basically the different servicers that we've built for our types. In this case, we had 2 types, account and bank, as well as any third-party servicers we wanted to pull in, which in this case, we pull in a collection servicer because we want to store effectively a distributed list, which is all the account IDs for the bank, as well as this Mailgun servicer. And then from that, those data types gets partitioned across your cluster. So I wrote a single file, .py file. You wouldn't have to write it that way in your own apps, of course. And then we take it upon ourselves to run all those types across your entire cluster in a completely distributed way. Okay, so account would be the natural one that as you add a lot more accounts, you'd want to scale that in your cluster. Okay, all right, that's all I had. This is the first time I'm speaking publicly about it, so super glad to be here and chat with you all. And yeah, happy to take a question or two, and then we'll wrap it up.
So I'm curious there, like it's easy to see this in the types you control, but when you're calling out to a third-party service, how are you avoiding two-phase commit?
Yeah, exactly, yeah. So for a lot of the third-party services you're calling out to, they don't have a two-phase commit. The APIs aren't that good. You have to do them eventually. You can't do them consistently as part of the transaction. So what's actually happening with Mailgun is we're effectively doing a dry run to make sure that this would work. And then we're scheduling an asynchronous RPC, which is part of the framework, and I didn't talk about it. That asynchronous RPC will only be executed if the transaction completes. Once the transaction completes, then we do the actual effect. With most third-party APIs, since they're not compensatable, that's how it works. If you have a third-party API that can be hooked into our two-phase commit, then you can do it that way. Then you can write a little bit more code to, yeah. That's why there's more magic there. But even with something like Mailgun, does not have the concept of idempotency. So how did our library solve the problem? It does have the concept of tags that you can attach to your emails. So we attach a tag to the email called idempotency key with its value. That's how we make sure that we don't send the email twice. One of the things I didn't mention, but in the back end, you might have seen this when you're looking at it, every single in dev mode, every single RPC that comes in, we execute twice. Why? Because we're trying to make sure that you don't screw up effects. If you've used React, you're very familiar with this in strict mode. Works great on the back end too. That's why it looks like we're, it says found already accepted email message. It's because we ran that function twice, emulating a failure to make sure that we only send an email to him once. And he only got an email once, right? He's only got an email. At least he got one. Okay.
So far.
Great. Okay. Thanks so much.